Welcome back, and in this series of videos we're going to be looking at chemical kinetics. So that's how fast the reaction goes. We're also going to be looking at how that relates to the mechanism. So we're going to start from your GCSE understanding and we're going to build on that. Kinetics is quite an important topic in chemistry. It's a yellow topic, so it goes in with the organic chemistry topics. So it's a paper 2 topic. So you can see from the front cover there's a lot of specification points that are connected with chemical kinetics. And this is only chemical kinetics 1. We've also got another pack, chemical kinetics 2. So you can kind of think of kinetics as the moles of the upper sixth. So it's got lots of different specification points. There's a lot of stuff you need to know and a lot of stuff you need to be able to calculate. So kinetics is the study of how quickly the reaction takes place. It doesn't tell us how much will be formed. That we study in equilibria and entropy. But it will tell us the rate at which the reaction will occur. Now, for the reaction to take place, two things have to happen. The particles of the reactants must collide. In other words, they've got to bump into each other with the correct energy. In other words, they've got to collide with an energy greater than or equal to the activation energy. But they also need to collide in the correct orientation. So it's no good them colliding with the correct energy if they're not orientated correctly. And there are 5 factors which affect the rate of the reaction. And you'll probably be familiar with these from GCSE. So we've got temperature, concentration or pressure. Those two basically are the same term. Concentration generally talks about solutions and pressure about gases. Surface area, so the higher the surface area the better. A catalyst, and one you possibly might not have come across before, pH. So here we have my 2 powders, lead 2 nitrate, it's white powder, and I also have potassium iodide, which is also white powder. I've added both of those to my boiling tube. You can see there I've got the lead nitrate on the bottom and the potassium iodide on top. And I'm going to give them a very good shake. You should see there that they've changed colour to a yellow powder. Now this is a very unusual reaction. This is what we call a solid-solid reaction. But I can get the reaction to happen faster if I, instead of shaking the 2 solids together, if I dissolve them in water, I can get the reaction to happen much faster. So here I've dissolved both of my solutions in water. So I have a solution now of lead 2 nitrate and potassium iodide. And all I'm going to do is I'm going to mix both of those into my boiling tube. And I've formed there my precipitate of lead 2 iodide, and that's that bright yellow powder that you can see in my boiling tube. So you've come across this mechanism before. It's the electrophilic addition mechanism of hydrogen chloride to an alkene, in this case ethene. So I've got the dipoles on here, so I've got my delta positive, delta negative, delta negative, delta positive. So I'm just going to put on my dipoles, delta negative, delta positive. So you can see here, this is the only orientation which is correct, because I've got the delta positive ends of my molecule pointing towards the electron-rich double bond. So that's going to pull the electrons from that double bond onto that delta positive. In these cases, you've got a negative approaching a negative or electron-rich area, so these two are going to repel. These are going to repel, and these are going to repel. So this is the only orientation that is correct. So there, the delta positive hydrogen is attracted to that electron-rich double bond, and it can accept the pair of electrons from the pi bond. In the other orientations, we'll get repulsion between the delta positive and the electron-rich carbon double bond area. It's not enough though for them just to react in the correct orientation. They have to also collide with sufficient energy. And we call that energy the activation energy. And that's defined as the minimum amount of energy that must be supplied to enable the bonds to stretch and break. And we can see that on the next page. So here we have our reactants. That would be our hydrogen and our chlorine, and they're reacting to form two HCl molecules. This is going to be my activation energy, so that's the minimum energy they need to overcome in order to react. And that up here, this maximum here, we've got 2 hydrogens and 2 chlorines, so we've broken the bonds. So this is the energy needed to break the bonds, and then the total energy we get out. So the energy is here, and that's the energy released when we're making the bonds. And the difference between those two levels, the start and the end, that is our delta H value. One last thing, this top bit here, the top of the curve, we call this the transition state. Transition state. It's different from an intermediate, and I'll come back to that later. And we can do the same thing for an endothermic reaction. So an endothermic reaction is very similar to our exothermic reaction. It will still have an activation energy, so there are our reactants, but it will still have an activation energy. It's just instead of ending up lower, we'll end up higher than our reactants. So our reactants here, you've got 2HI, and our products here, we have H2 and I2. We still have this activation energy here to the top, to the maximum, that is EA, and we still have our overall delta H, and this time the delta H is positive, pointing the arrow that way, delta H. Here again I've got my transition state going through the individual atoms. So this is bond breaking, bond making, but this time it's an endothermic reaction. So in this next section of the notes, we're going to be looking at the factors that affect the rate of the reaction. You've come across many of them before at GCSE level, so I'd like you to have a go at filling out the next 2 pages on your own. So what I'd like you to do now is to pause the video, have a go at doing that, and then I'll go through them with you. So the first one we're going to look at is the effect of concentration. So I've got low concentration, high concentration. I've simply got more particles in my high concentration. So there's more molecules per unit volume. In other words, there's more particles in a given space. So there's going to be a much greater chance of collision. And that means there's going to be more collisions per unit time. And you have to be careful to specify the time part of this. What you need to understand is that the rate, and I'll come back to this later on, is equal to the change in concentration over change in time. So we always talk about a factor of time, per unit time or per second or per minute or per hour. So the surface area, we have the same argument. With the larger surface area, by turning it into a powder, we get more surface for the molecules to attack, and again we get more collisions, again per unit time. So here we have an example of increasing the surface area. I have woods, which I've ground to a very fine powder. And in my second example, I have iron filing. So again, iron that I've turned into a very fine powder. So it burns a bit like a sparkler. Temperature is an interesting one because there are actually 2 reasons why increasing the temperature will increase the rate of the reaction. Firstly, the molecules are moving faster. They have more kinetic energy. So they're going to bump into each other more frequently. But that's not the overriding factor. The overriding factor is that because you've increased the kinetic energy of the molecules, more of those molecules will have an energy greater than or equal to the activation energy. In other words, they will be able to overcome that barrier. And therefore, there again be more successful collisions per unit time. Notice the change here from just more collisions to more successful collisions. And that's an important distinction. Last but not least, pressure. Now, pressure is exactly the same as concentration, but for gases rather than solutions. But the arguments are the same. So we've got more molecules per decimeter cubed, more molecules in a given volume, so there'll be a greater chance of collisions. So there'll be, again, more collisions per unit time. So we can show some of these effects on what we call a Maxwell Boltzmann diagram. So if we think about the molecules in a gas, they are moving rapidly and randomly. But they don't all have the same energy. So no, they don't all have the same energy. Some will be moving faster than others. Now, the Maxwell Boltzmann distribution shows us the statistics. So it's basically showing the distribution of molecular energies. It's not telling us the energy of any individual atom or molecule, but it's showing statistically what a sample of a gas would look like. So the total number of molecules of gas is shown by the area under the curve. So that's area under the curve. The number of molecules with an energy greater than or equal to the activation energy is shown by this shaded area. Or basically the area to the right of the activation energy line. So this part of the graph here. These molecules, doesn't matter how many times they collide with each other, they're not going to react. Only the ones with the correct activation energy will be able to react. So there are a couple of things to notice about these, and it's important that you can draw them accurately, even though they're a sketch graph. No molecules have zero energy, so you always start at the origin here. It's a classic mistake that students start their chart in the wrong place. You must always start at the origin. Few molecules have very high energy. In fact, there's a very, very small probability of finding a particle with an infinite amount of energy. We don't in real life, but statistically, this line never crosses the axes. It just gets closer and closer to it the further you get along the axes. The area under the curve, as we said, represents the total number of molecules, and only the molecules in this shaded area have sufficient energy to react. So in kinetics, what we can do to improve the situation is one of two things. I can change the shape of the curve so that I get more particles in this part of the graph, or I can shift the goalposts and I can lower the activation energy. And we're going to be looking at both of those in the next section. So a fast reaction has a low activation energy, which is shown by a large shaded area on my graph. Every reaction has an activation energy. Reactions that simply go spontaneously still have an activation energy. It's just that the activation is so low that most particles at room temperature would have an energy sufficient enough to overcome it. So we've got here our Maxwell Boltzmann diagram for two different temperatures, T1 and T2, where T2 is higher than T1. So here is my low temperature curve, and here is my high temperature curve or higher temperature curve. They're still going to start at the origin, they're still going to have the same general shape, but a couple of things you do need to notice. This T2 line, the peak has moved to the right because the average energy is now higher. It's lower, it's more, if you like, spread out in terms of the energy levels that my particles can take. But the key thing for us to notice is this end. If you see where the activation energy line is Originally, only this small number of particles here had an energy sufficient to react. But now I've increased the temperature, you should be able to see that a lot more of those particles are therefore able to react. So the peak moves to the right. You've got more particles with an energy greater than or equal to the activation energy. Now, when you come to answering exam questions about the effect of temperature on the rate of reaction, you have to remember that there are two things which are changing. Firstly, the particles will simply be moving faster, so you're going to get a higher frequency of collisions. In other words, you're going to get more collisions per unit time. Also, those collisions will have higher energies, so a greater proportion of collisions will have an energy greater than or equal to the activation energy. And it's this one that's the most important factor. It's the fact that you've got more particles in this shaded area here. That's what makes the rate of the reaction increase. There's still an effect coming from the frequency of collisions increasing, but it's not as important as the fact that those collisions have higher energies. So that finishes off this video, just looking at the first section of Kinetics 1. So you need to understand the factors that affect the rate of the reaction. We've looked at a Maxwell Boltzmann curve and how temperature affects the rate of the reaction. In the next section of the notes, we're going to be going on and looking at how we measure the rate of a reaction.